My name is Alan Wolke. I'm a Field Application Engineer with Tektronix. And in this webinar, we're going to take a look at how to get the most out of your touchscreen oscilloscope. Let's get started. We're going to be using the new 2 Series Mixed Signal Oscilloscope, but all the concepts presented here are fully applicable to all of the Tektronix touchscreen scopes. We'll start off with the basics, the user interface and all the controls, and also talk a little bit about how to avoid some of the common pitfalls and things people forget about when setting up their scope. Then we'll dig in a little bit deeper and look at things like zooming in on waveforms, uncovering waveform details and searching for various defects and things like that. And then we'll talk a bit about remote control of the oscilloscope, so you can drive your scope and not have to be in front of it, and how to share data that you've collected with your colleagues. So to get started, let's first look at just setting up the scope. We'll start off by looking at some of the features of the touchscreen interface and how to control the various menus and how to use your fingers to do the driving. Because of the intuitive touchscreen interface, you may find that you already know how to drive this scope. Then we'll dig into some more details on the vertical controls and look at a couple of often misunderstood controls in that vertical setup. We'll take a look at the horizontal and acquisition controls and help you better understand what those things can do. And as well as the trigger controls, we'll dig into those as well. And we'll also talk a bit about probes. Most of the time you're using a scope with probes, and there are a couple of important aspects to think about to avoid adding distortion and to get accurate results using your probes. So let's dive right into our first hands-on session.
Let's begin with the basics of the user interface of this touchscreen scope. You've got your familiar buttons and knobs. You've also got a large touchscreen interface that becomes very intuitive to use. So let's take a look at the fundamentals. The combination of the touchscreen and the buttons and knobs means that in many cases there are 2 or even 3 ways of accomplishing any given task. So you can tailor the way that you use the scope to the way you're comfortable with operating an oscilloscope. For example, adding another channel can be done as simply as touching the button on the front panel to add a channel, or touching the badge or icon on the screen to add a channel. Now you may notice that this is a 4-channel oscilloscope, but there is only one set of vertical knobs for scale and position. So the way you can determine which channel those knobs are being used for at the moment is look at the illuminated ring around the position and scale knob. You can see right now that it's illuminated red. That's the same color surrounding the channel 3 button, and the same color that shows up here on the silk screen and the trace color on the screen. And we can also see that channel 3 is the active channel because its reference indicator is highlighted. So if we change which channel is the active channel by either hitting the front panel knob or touching the screen or touching the badge, we can see that the illuminated ring will change based on the active channel. Now similarly, the illuminated ring around the trigger level control will illuminate in the color that's corresponding to the channel that's being used as the source for the trigger. To remove a channel from the display, just like the old scopes, you could touch the channel to highlight it, touch it again to get rid of it, but also on the touchscreen you can simply drag the badge off the screen. If you choose to, you can attach a mouse and keyboard to one of the USB ports and use that to interact with the scope. In addition to supporting single touch and drag controls, the scope also supports a multi-touch for pinch and zoom operations, both horizontally and vertically. The pinch and zoom operations can leave you with some odd vertical and horizontal scales, so you can always go back to the knob-based controls to get to the more familiar detents. And many of the knobs, such as the vertical scale, allow you to push them to go into a fine mode to get a finer adjustment on those detented settings. Many of the badges support both single and double tap operations. A single tap will often bring up the most commonly changed items on that particular badge. In this case, single tapping one of the channel badges brings up the vertical size or vertical scale control. In the case of the horizontal badge, this will bring up the horizontal scale controls. Double tapping on the badge will bring up the full panel for that particular function. Each panel can be repositioned and is also semi-transparent so you can still see what's going on behind your panel. A single tap outside the panel removes it. Many panels will have a couple of pages to them. Here we have the main vertical settings, and then if we touch down here, we open up the probe setup panel. This blank area over here is where the measurement results will show up when we add measurements. We'll do that later. But if you're not going to be adding measurements and you want to maximize your waveform viewing area, you can simply tap on these three dots on the right edge of the display and collapse that panel temporarily. Simply tapping on it again will open up that panel. Now you may have noticed when we added a new channel, that channel got added in its own slice, a separate radical. And the reason for doing this is to maximize resolution for each waveform. The analog to digital converter behind each channel is essentially spread across the entire radical for that channel. And by adding each new channel in its own radical, you can maximize the resolution for each waveform without overlapping the waveforms. We call this the stacked mode of operating. Many users are accustomed to stacking waveforms on a single radical. They do that by reducing or increasing the volts per division to reduce the waveform size and then adjust the position of each waveform so they didn't overlap. The downside to doing that is that you're not getting the best resolution on each waveform because you're not getting close to the full scale of the analog to digital converter. This stacked mode allows you to get the best resolution and still keep the waveforms separate from each other. So if we add a third channel, we get yet another slice, and all of them are stacked on top of each other. Now certainly there are applications where you'd rather have the waveforms overlaid, and we call that the overlay mode. We can change the mode to overlay by simply holding on the display, hitting Configure View, and selecting Overlay. And now all the waveforms are overlaid on top of each other, just like your old school scope looked. A long touch on the display, and select the shortcut for stacked, and we're back to our stacked view. You can also very easily reorder the stack by simply dragging the badges around. If I want to put channel 2 on the bottom, I simply grab its badge, move it, and drop it behind channel 3. Now there may be situations where you want to overlay some channels but not all, and you can do that as well. For example, I might want to overlay the channel 2 clock signal here on top of that data word. I simply take its badge, lift it up, and drag it down on top of the channel 1 badge. And now those two channels are overlaid, and I'm stacked on the third channel. To revert back to stacked, simply take the channel you want to pull out of the stack, let go of it, and it reverts back to a full stack. Each of the badges along the bottom of the display operate a similar way. If I touch on the horizontal panel twice, I could bring up all the horizontal settings here and the acquisition settings in that drawer. If I double tap on the trigger badge, that brings up all the trigger selections. That should get you started on some of the aspects of this touchscreen interface. Let's focus now on fine-tuning some of the controls to get the most out of your waveforms. Let's take a look at one of the lesser-known but very useful features of the vertical menu. I'll turn off channel 2. I'm going to reposition my probe on channel 1 to a different voltage here. And we can see we've got a voltage that's sitting around 1.1 volts or so. And if we take a look at a little bit more data here in time, we can see there's a small variation on that signal over time. So what we want to do is expand and look at that. What most users would do is adjust the scale and say, well, okay, now that signal is up above the, or getting closer to the top of the screen because I'm expanding around my reference point here, which is at ground. So I'll use my position control, or I'll drag down with my finger to kind of get that closer and expand the scale again. And now that signal is above the screen and I can't get to it with the position control anymore. So what do? Well, we could use AC coupling, but that might remove some low frequency content, so we might not want to do that. So let's get our signal back here on the screen again so we can see what's going on. And let's take a look at the vertical badge. Now the vertical badge has got two controls on here. Position, which is what we've been using with the front panel and by dragging, but there's also a feature called offset. What offset says is where this reference point is. So this C1 indicator right here is right now sitting at 0 volts, and that's the default position. And there's a little preset to get you there. But that's also the vertical expansion point, meaning when I adjust my vertical scale, I'm expanding around that point. So we can move that reference point using the offset control. We know the signal is sitting at about 1.1 volts, so if I go and change this offset to 1.1 volts and hit enter, now I can see my signal centered near there. I can bring that closer to the center of the screen now with my position control, and now if I adjust the vertical scale, I can expand around that waveform very easily, where I wasn't able to do that before. Now again, the beauty of using that offset control is it allows you to set up and adjust your scale around your desired reference point without relying on AC coupling to remove that large DC offset. So now you can see small and long-term changes in the DC level along with the high frequency variation that we're seeing here. Now another thing to think about is the bandwidth that's being used to measure your signal. In this case I could see there's some variation on this waveform and there's a lot of noise on it as well. But we're looking at a 500 megahertz bandwidth. So if I go into my badge here and I change the measurement bandwidth, well, let's say if I go all the way down to say 20 megahertz, now I've knocked a lot of that noise out of that waveform and it makes it a lot easier to see what's going on. So the lesson here is get to know some of these other controls, such as the bandwidth control, use what's appropriate for your waveform, and the offset control, which can really help you look at small signal variations sitting on top of a larger DC bias. Now it's important also to pay attention to some of the information that's in each of these badges. For example, the horizontal badge tells us our time per division. It tells us what sample rate the waveform is being stored at. It also tells us what record length is being used. If we double tap on that badge, we can see that that horizontal mode is set to automatic. What automatic does is, depending on where you set your horizontal scale, it will determine what sample rate and record length to use to give you a decent representation of your signal. However, if you want to set the sample rate or the record length manually, you can go into manual mode and you've got the ability to set all of those things yourself. At the top of the screen here we see the word sample. And that refers to the acquisition mode. That can be found under the acquisitions panel right here. There's our acquisition mode. Now here's what sample mode means. Now this scope can sample at 2.5 gigasample per second. But we can see on our badge we're only using 50 megasample per second. So what sample mode does is it's throwing away all those samples in between our 50 megasample per second spaced points. That's what sample mode does. The other available sample modes do other things with those samples. Peak detect will take a look at all those samples that would normally get thrown away and find the highest and lowest values and place those for each acquisition. The envelope mode does the same thing, but continually accumulates that over time, so you build up the peak-to-peak value over time. The average mode will average multiple acquisitions together to essentially reduce the random noise. And then finally, the high-res mode takes all of those samples that would normally be tossed away and averages them together to a single point. So it's kind of like an in situ averaging. And we can see that will reduce the amount of variation even further. The other side benefit to high resolution mode is it gives you more vertical resolution than the ADC gives you by itself. And as always, the acquisition mode is indicated here on the top of the display on this scope. The trigger settings are accessed by double tapping the trigger badge. The vast majority of the time, a simple edge trigger is all that's used, but there are other trigger types, and each one of them will come along with a little bit of a picture to kind of show you what that trigger type is doing and how you set it up. One often misunderstood feature in the trigger system is something called the trigger mode, or specifically the auto trigger mode. Now, contrary to what many people think, auto trigger does not automatically set up the trigger. It's a visibility aid. And the way it works is this. The scope is looking for a particular trigger event. If that event doesn't happen within, say, 50 to 100 milliseconds, the auto trigger will self-trigger the scope. And the result is you'll get a waveform on the screen. It may not be synchronized, but at least you'll get something active on the screen, so if you're moving your probe around, you'll see what's going on. And it might then allow you to fine-tune your setup, fine-tune your trigger condition, so that you can actually trigger on a particular aspect of your waveform. We could see here, for example, I've got an edge trigger set up here just below 1.22 volts that's triggering on that edge. If I move my trigger level up above the waveform, now I can see I've got an untriggered rolling waveform around here. There's nothing lined up at my trigger point. So that's what the auto trigger does for us. If I bring this back down, now I'm triggering back on this again. If I switch to the normal trigger mode, everything is working fine here because I'm actually meeting my trigger condition. If I move my trigger level up again above the waveform, now we can see the waveform is sitting still. So I can't tell if the scope is frozen or something wrong with my circuit or whatever because I'm not getting any update on the screen because the input signal is not meeting my trigger condition. This is where the auto trigger can be helpful to make the waveform live so you can then fine-tune your trigger conditions or input conditions to get what you want on the screen. So don't be confused by auto trigger. It doesn't automatically set things up, it just helps you see what's going on. The next tip I want to talk about has to do with probes, and the two most common things with probes that are often neglected by both new users and experienced users alike. The first of those is properly compensating your 10x probes. When you received your 10x probes, it probably came with a little tool like this. This is a probe compensation adjustment screwdriver. Now, how many of you know where this is? This should be stored right along with your probes because probe compensation is very important. The compensation adjustment ensures that that probe is properly matched to the input capacitance of your scope. Anytime you change probes between different scopes, you should recompensate that probe. If it's not compensated properly, any amplitude measurements made on signals above just a few tenths of kilohertz will be incorrect. All scopes will provide a probe compensation signal available right on the front panel. The probe compensation signal is essentially a 1 kilohertz square wave, and the idea is that you would stick the adjustment screwdriver into the probe and adjust it to get as perfect a square wave as you could possibly get and not be overcompensated or undercompensated. And this will equalize or match the scope's capacitance with the probe capacitance and give you a good flat frequency response over the bandwidth rating for that probe. Another very common mistake is to not pay careful attention to the ground lead length. This ground lead can add inductance into the measurement path, and that inductance can ring against the circuit and probe capacitance and cause ringing on a waveform such as this. We're looking at a short 2 nanosecond pulse and some ringing that's all due to that ground lead length. The probes will often be supplied with additional ground accessories like this little spring clip, and this is designed to slip onto the end of the probe right onto the coaxial ground ring, and this will make for a very short ground return path for the probe. Now here's that same signal being probed with a second probe using that very short spring lead. We can see almost all of that ringing due to that long ground lead has now gone away. This is a bit of a tip of the iceberg on proper probing techniques, but certainly two of the most common things that are often neglected, again, by both new users and experienced users alike. So please pay attention to how you're probing your signals.
Now that we've got the basics under our belt, let's dive a little bit deeper. We'll take a look at zooming and panning your waveforms to look at finer details. We'll use waveform cursors to extract specific measurements off of our waveforms. And we'll talk about measurements in general and how to set them up and optimize them. We'll dig into the math system to understand how you can derive your own waveforms from your acquired data, and also use search and mark capabilities to uncover hidden details and help you identify how often those things occur. And finally, we'll look briefly at mask testing, another feature that can help you understand variations that might happen in your signals. So let's dive right into our second hands-on session.
The first thing we'll take a look at as we dive a little deeper is zooming in on a waveform. And as you might imagine, there are many ways of doing that. So if you look carefully in the upper right corner, you'll see a small magnifying glass. If you touch on that, it brings up a zoomed area. You'll also notice that the A and B knobs are now illuminated, indicating that they've got some function. And we can see here that the A knob will adjust the horizontal zoom level, and the B knob will adjust the position. And the full complete waveform is shown at the top, and the zoomed in area is what's shown down below. Of course, we can manipulate this with the touch as well. And notice if I pinch and zoom, it changes the size of that zoom area. And if I drag back and forth, I can move that zoom area. And I can also move it right on the top view as well. Now, of course, pinching vertically will also zoom in vertically. And again, I can position that in different spots of the waveform, both in the top view as well as down in the waveform view. Pinching vertically is the same thing as hitting the plus or minus on the V zoom controls right here. Of course, there are other ways to initiate the zoom as well. So we'll hit the X right down here to close the zoom area. We'll look at another way to initiate zoom. This icon right here allows you to draw a box or a region on the screen. And it can be done for a couple of different purposes. It can be done to initiate a zoom. It could also be done for mask testing. We'll select zoom in this case. Now with that highlighted, I can simply draw and drag a box on the screen, and when I let go, that's my new zoomed in area. That can be further refined by zooming in on the area again, just to grab the particular edge or feature of the waveform that you want. In this case, this tiny little overshoot just before that fall. So essentially all of those intuitive pinch and zoom moves will initiate zoom and move things around in a very intuitive way. Another very common feature on digital scopes is cursors, and we've got them here as well. In fact, the button is located right here. We just touch on cursors. That adds a pair of cursors to the screen. Those cursors can be manipulated any number of ways. We can touch and drag them very easily with our finger. We can use the illuminated knobs to move them back and forth. You'll notice that the fine indicator is illuminated on both. If we push the button, the fine goes away, and that will move it in a much faster or coarser step size. And when we push it again, it goes back to fine, and then that cursor will move much more slowly with the knob. The readouts for the cursors are shown, both for each cursor as well as for the delta. If those readouts are in your way, you can simply touch on them and move them so they're not overlapping your waveform. Touching and holding on the cursor readouts will bring up a small menu where you can turn the cursors off. We can also change the cursor type. We're currently using waveform cursors, which pick out points on the waveforms, but we can also set up vertical and horizontal bars. And under the configuration for the cursors, one of the things we can do is have those cursor readouts come up over here on the badge area, as opposed to being up on the screen. So if they were in your way entirely, you can certainly move all those readouts off to the side. Here you can also choose whether the cursors are going to be on the same waveform or split between two different waveforms. Now, one thing I'll mention here that's really common throughout the interface is anytime we bring up any one of these configuration panels, there's typically a question mark in the upper right corner. Touching on that question mark will bring up the help page for that particular menu item. One of my favorite features for documenting your work is this call-out feature. If we touch on this call-out button, you'll notice it put essentially some screen text on the screen. I can add as many of those as I want. If I double tap that, I can put in my own text here by double tapping here and using the keyboard. You can also play with the format in terms of font and font size and color and customize any of these text labels that you put on the screen. But in addition to screen text, and we call those a note, there are other options here as well. The arrow, I will add an arrow to that text that we just added. And you can take and grab that arrow and have it point at any feature you'd like on the screen so that you can point out something particular when you're trying to document what you're doing. The next type of callout is a rectangle, which draws obviously a rectangle on the screen that we can resize and position wherever we want to highlight some certain feature on the screen. Now, my favorite type of callout is the last one, called a bookmark. The bookmark can be considered like a little probe. And we can see here's the text, and there's actually a voltage reading, and I can position where I want that measurement to be made in time. So at this location in time, the voltage at that point in the waveform is being shown immediately. And I can add as many of these bookmarks as I want to get essentially voltage probe measurements at any location within the waveform. Of course, one of the huge benefits of digital scopes is automatic measurements. And we just touch the measure button here to bring up the measurement dialog panel, which includes all the amplitude measurements and time domain measurements. If we want to add a measurement, I can just say double tap the rise time, that adds that measurement, or tap it and hit add. I just added the fall time measurement. Very, very simple. With this interface, there's no limit to the number of measurements you can add. Once you fill up this badge area, you'll essentially get a scroll bar. You can scroll through all of those measurements. Once you've added the measurements you want, you simply can double tap each measurement badge to further configure it. We can add the statistics into the badge. We can change things like the reference levels that are being used to make measurements, and even include gating to define where you want that measurement to be made. Either no gating, meaning the measurement is applied across the entire record, or you can apply some other type of gating based on the zoomed in screen area, the position of the cursors, as well as just time gates that you can turn on and off. This gating can be applied globally to all of the measurements you've defined, or locally to one measurement at a time. If you've got a lot of measurements turned on, it may be helpful for you to add a results table. The result table will show you every measurement that you've made, its label, and its statistics. Now there's actually two different types of statistics here. These statistics that are marked with the hash mark, or the apostrophe, are statistics made on each acquisition. So for example, for the rise and fall time, I can see that I've got a population of 10 or 11 edges depending on what the waveform is coming in here. So this is the mean, min-max, standard deviation for those 10 or 11 measurements that are appearing on each acquisition. If I slide this table over, I've got another set of statistics, and these are accumulated statistics. They're added to with more and more acquisitions. So we can see in the time that we've been running here, I've got over 30,000 rise times, 30,000 fall times, 11,000 pulse widths, etc. that are all added into these accumulated statistics. Another important aspect to the way the measurements are made is that the measurements are applied to the waveform record regardless of how many points are actually shown on screen. So for example, at this horizontal setting here, I've got a 50,000 point waveform record. Obviously I don't have 50,000 pixels across the screen, but the measurements are made on that full waveform record. So the measurements that we're getting are all still valid. You will find that many scopes in this class don't do that. The measurements are always made on the on-screen pixels and not the actual waveform record. In this case, the measurements are always accurate because they're always made on the full waveform record. The math system in the scope can be used for a number of different purposes. If we add a new math channel, the default is a simple addition or subtraction of two channels. That's your very basic math type. And we can see that waveform here, adding these two channels and creating this math waveform. Now, of course, all your measurements can be applied to the math waveforms as well. But in addition to this very simple combining of two waveforms together, the math system also includes, of course, the fast Fourier functionality to give you the spectral response of any of the given channels. It also features an advanced math system where you can actually go in and edit an equation using the waveforms as sources, various functions including integrals and differentials, and all of the algebraic and even logic functions and numeric values as well. You can create a very complex expression to represent a particular parameter that's derived from your measurements. Now, observing this waveform, we can see that every once in a while we get a narrow pulse width here. Of course, we can isolate that with the trigger system by using a pulse width trigger. And let's look for a pulse width that falls less than, say, about 90 nanoseconds. And by doing that, we've now isolated that particular event. Now let's say we want to know how often that anomaly occurs in a long record. I can go grab a long record of data here and then enable a search feature. And in the search, I'm going to copy my trigger settings, because now I'm triggering on that event. I want to copy the trigger settings to the search criteria. And by doing that, I've now seen that I've caught two events. We capture a little more record of data in time. Now I've got 6 events, and we can see that they're marked here now. Now that we know the search has found those events, if we pause the scope, touch on the search badge, we can actually navigate to each of those events one by one, and the scope will zoom in on each of those events. If I double tap on the search, I can also turn on a results table, which will also show me where all those events occurred, at what location and time, and the delta time between them. And one final feature we'll take a look at is mask testing. If we touch on our More button here, we can see that drawing a box can be set up to do a zoom that we did earlier, or to draw a mask. So with it selected to draw a mask, I can essentially draw a box on the screen. That becomes a mask area. And we can see that right now we don't have any waveforms crossing that mask. And I can edit that. I've got a simple rectangular area now that I can touch on to drag and move around. I touch on it again, and now I can actually change its size by grabbing any of the edges or the corners. I can touch it again and move just individual vertices around. If I touch it again, I can add vertices on any of the legs. If I touch it again, I can actually rotate that around. And then touching it again cycles through all of those options. So you have a lot of flexibility in creating these mask areas that are customized to your waveform and what you're trying to look for. So with that mask defined, we can go into the mask test and actually turn it on. And now we'll actually get a count of how many times that mask actually gets violated or crossed. And of course we can just redefine that mask and move it around, and then again start counting up hits of when that mask gets hit. You can add multiple mask segments to test even more complex waveforms. So in addition to creating one or more mask segments, you could also define the mask based on the waveform that's shown on the screen by setting up essentially some waveform tolerances. And that makes it very easy to say, this is what my waveform is supposed to look like. Anytime it violates that, I want to count that every time that happens. So this allows you to set that up very easily. I hope these demonstrations have given you a little bit of a glimpse into some of the advanced features of the touchscreen oscilloscopes and how to help you get the most out of your measurements.
In the final hands-on session here, we'll take a quick look at remote control and data sharing. We'll talk about using VNC for remote control. We'll also take a look at TekDrive, which is Tektronix cloud storage service to allow you to share data amongst your colleagues. We'll also talk a bit about TekScope for offline data analysis. So let's dive right in. Let's first talk about remote control. The 2 Series MSO uses VNC, Virtual Network Computing. There's actually a server built into the scope. We're actually using it already here, but I'll show you how you enable it. You go into the utility menu and select I/O. And on the first LAN panel here, we can see the IP address that's being used. It was automatically selected. You can also manually select the IP address. And the panel along the bottom is the VNC server, and you simply turn it on. You can optionally include a password to restrict access. Once you've got it turned on the scope, all you need to do is run a VNC viewer on your PC. I happen to be using Tight VNC, as we can see here. I find it working very, very well. It's very fast and very lightweight. Now once this is running, as you may recognize, the user interface here is identical to the user interface when you're sitting in front of the scope, and all of the controls that would normally be available to you on the scope itself can be used virtually. And a number of users can dial into the scope at the same time and be viewing what's going on simultaneously. Other touchscreen scopes in the Tektronix family use VNC generally when the Windows operating system is included, like on the 5 and 6 series scopes. And then on the non-Windows, like 4, 5, and 6 series scopes, there's another utility that's available called eScope. And that's essentially a web server that's built into the scope. And you simply take your web browser from your PC and point it to the IP address, and you get an LXI page that allows you to select eScope, and then the display and user interface for the scope will come right up on your web browser. So depending on which scope model you're using, either VNC or eScope is your key to operating the scope interactively from a remote location. Next, let's take a brief look at TekDrive. TekDrive is a cloud service offered by Tektronix that allows you to store data in a centralized cloud-based location and share it amongst your colleagues and access it from anywhere in the world. Let's open up my TekDrive. So I've already logged into my TekDrive, and we can see under My Files I have 2 files stored here already. These are session files that were stored previously from my oscilloscope. Let's bring the scope up and save another one to the TekDrive. So now we're looking at my scope here again. If I go under File Utilities, I can see the drives that are available are the internal drives in the scope as well as USB drives, and I've already mounted my TekDrive here. So now that the tech drive is mounted, I can go and save files to it. So for example, if I go in and do a save as and save a session file. Now a session file is a file that contains all of the acquired waveforms and the setup of the scope. Makes it real easy to share what you're measuring with a colleague. So tell it I want to save a session file, and I've already browsed to my tech drive to save that file. And let's call this test1 and hit save. That will save that session file to my tech drive on the cloud, and you'll see it show up automatically here now on my tech drive. You have the ability within tech drive to open that with a couple of utilities that are available to look at the waveforms and extract data, and you can also choose to share this file with a colleague, and that will show up in their tech drive under Files Shared with Me. So tech drive makes it very easy for you to store data in a central location and make it easy for you and your colleagues to go access it later on. And finally, let's talk a bit about Tekscope. Tekscope is a PC application, which is essentially the user interface from the touchscreen oscilloscope running on your PC. With Tekscope PC, you can read in data that was collected by other scopes, even read the data directly from tech drive, and even connect up to other network connected scopes and pull data directly over. You can, once the data is loaded in Tekscope, you can add measurements and do all the things you can do with data that was acquired in the scope. Let's go take a look at it. So here is Tekscope running on my laptop. As you'll notice, it looks very much like the user interface on the oscilloscope itself. Let's briefly pull up my VNC of my connected MSO2 to see what's going on the scope. Okay, so here's what's going on live on my scope. Let's actually pull this waveform directly into Tekscope PC. So I'll go down here to the bottom where it says Add New Scope and click on that, and let's put the IP address in for my oscilloscope and hit connect. Once that's connected, we can see the waveform get pulled immediately into Tekscope. Once it's here, I can do things such as add measurements. If I want to measure rise time measurement, for example, I can add that in here. I can add my fall time measurement in here, and all the other operations that we want to do with the scope we can do directly right here within Tekscope. We also have the ability to tie in to tech drive. So I can mount tech drive right into Tekscope here, and let's say I want to recall that session file that I just saved a little bit earlier. I'll go into Sessions, and let's go tell this to look at tech drive and go down to My Files, and there's test1 that I had saved into my tech drive, and we'll recall that back in here. And now that session file that I had saved to tech drive from the scope is now pulled into my offline Tekscope PC for further analysis. And colleagues that you work with can do the same thing no matter where they are located, as long as they've got access to the internet to grab the data off the cloud. As you can see, the Tektronix touchscreen oscilloscopes give you a lot of flexibility in remote operation and data sharing and collaboration with your colleagues. I want to thank you for watching today's webinar. Hopefully you learned a bit about how to use the touchscreen scope and to make the most effective measurements and to dig into the details of your waveforms, as well as how to collaborate with your colleagues, operate your scope remotely, and get the most out of your experience with your new touchscreen scope. Be sure to visit tek.com to find out more details on the products shown today. Thank you for watching.